Hello, IB students. Today we're going to take a look at a projectile motion. Alright, so projectile motion, a very important concept in IB physics, and it describes the motion of any object which you throw from a planet. For example, Earth. For example, this plane, when I throw it up and its trajectory until it falls to the ground will be projectile motion. Alright, so why do we investigate in projectile motion? Well, it's basically that we've learned about uniform accelerating motion last lecture, and that describe any motion which have a constant acceleration to it. However, uniform accelerating motion is a little bit more complex than uniform motion itself, because uniform motion only allows the object to travel in a straight line. However, when I'm saying uniform accelerating motion, my acceleration can either be the direction that is on the line of my velocity, or have an angle to my velocity, or be completely perpendicular to my velocity, right? So these are the three scenarios which my acceleration can have, right? So these three scenarios actually, the SUVAT equation we've talked about in our last lecture, they apply to all three of the scenarios. However, these all three scenarios are very interesting, and they are completely different when we look at them separately. Okay, so when my acceleration is in the same direction as my velocity, for example, when the plane is accelerating, or when the pin is directly falling to the ground, my velocity is strictly equal to at. That's the simple part, right? It's very simple. Or just v equals vi plus at. That's the one-dimensional motion which we've already investigated in the last video. However, if my acceleration is perpendicular to my velocity, say I'm going north and my acceleration is to the west or to the east, in this case I will be traveling with the uniform circular motion. Alright, so my trajectory will be a circular path. Alright, so this is the kind of motion that our planet, the sun, the moon, or our earth is experiencing. However, today we're going to look at the scenario where our acceleration forms an angle with our velocity. Right, so for any projectile motion, say this is an apple and it gets hit up to the ground, so it gets throws off the ground, so its initial velocity should form an angle to the horizontal ground. So this is its initial velocity v, right? So let's think about it. As it is traveling in the air, this is still its velocity, right? And what is its acceleration? Well, the only acceleration is the acceleration due to gravity, which is from the earth. So its acceleration will be this way, a, which we've also denoted as a little letter g, right? So we use the letter g to denote gravitational constant. So these two clearly forms an angle and is not perpendicular, so it belongs to projectile motion, which is what we're going to investigate. Right. Similarly, if I were standing on the tall building and if I throw an apple directly downwards, and it's at the same time I throw it downwards, it's also experiencing gravity, right? So this is the gravity it's experiencing, and this is its velocity, and it forms a very sharp angle. This is still projectile motion. Alright, so there are actually a lot of things we can investigate about projectile motion. For example, if I throw an apple off the ground and if it travels up until it falls back and hit the ground, well, how far it has traveled according to the ground, or what is the maximum height it can reach, or how many seconds does it take for it to go up and fall to the ground, right? What's its traveling time, and also what is its velocity when it finally hit the ground, all right? So I want to calculate, when I hit the apple and hit someone, how painful will they feel, right? So that's the things I'm kind of investigating here. All right, so first of all, let's look at the range. Well, when I throw an apple, how far it will have to travel, right? So when I only look at the diagonal velocity, I cannot say anything, I cannot make any progress. Thus, we use a very important tool called vector discomponenting. All right, so we essentially decompose the vertical velocity, the diagonal velocity, into a vertical component of it, which is v vertical and v horizontal. All right, so this is the basic vertical componenting knowledge in middle school math. You should learn about it. You should also learn about sine, cosine, trigonometry. Those stuff will be very useful in this lecture. All right, so So when I discomponent my actual velocity into the horizontal section and the vertical section, I have two very useful information, right? So, the only acceleration I'm experiencing is the acceleration due to gravity, right? So my horizontal velocity essentially tells me how fast am I covering distances on the horizontal level relative to the ground. So, for example, if I'm throwing this stuff 60 meters, to the air, I might be covering a lot of vertical distance, right? I might be traveling very high. However, the horizontal velocity does not care about how high I have traveled. It only cares about how far I have traveled in the horizontal direction parallel to our Earth, right? So this is the horizontal velocity. If my vertical velocity is 4 meters per second, my horizontal velocity will be 2 meters per second, because this is basic trigonometry, right? So, and my vertical velocity will be 2√3 meters per second. So what this means is, if the apple is traveling 4 meters 60 degrees relative to the horizontal, it will have traveled 2 meters on the horizontal level every second, and it will raise 2√3 meters. And what this essentially means is that the object will be 2 meters further out every second and 2√3 meters higher every single second, right? So this is the meaning and explanation of vector discomponenting. All right, so when I look at this graph, I see that the only acceleration my object is experiences is in line with my vertical velocity. So this goes back to the one-dimensional motion, which we've already mentioned in our last video, right? So this is very easy to investigate. And another thing I see is my horizontal velocity is not affected by any acceleration. So in the whole time my apple was in the air, or in the whole air time of my apple, its horizontal velocity does not change. This is a very important thing, because the only thing that is deciding how far the apple will have traveled is its horizontal velocity, right? So to calculate the range of my apple, I will just use my horizontal velocity times how long my apple have traveled, right? Times the time, because only when the apple is in the air does it move, right? But what decides how long my apple will stay in the air? Well, it is its vertical velocity, right? Because the higher I throw the apple up, the longer it takes for it to hit the ground. So my distance will be equal to my horizontal velocity times time. And what is my horizontal velocity? Well, it's basically my actual velocity times the cosine of this angle, right? The cosine of this 60-degree angle. All right, so basically what it looks like is this. This diagonal line is my actual velocity, and this vertical line is my vertical velocity, and this horizontal line is my horizontal velocity, and this is the angle I'm looking at, which I call it theta. All right, so basic trigonometry will tell you that my horizontal velocity is just the theta angle of my actual velocity. All right, so it will be used to time the time of my apple which is traveling in the air. Well, how do I investigate how long my apple have traveled in the air? Alright, to investigate about the time which it takes for the object to hit the ground, we need to understand a very important concept, which is that the projectile motion is essentially symmetric in respect to time, which means the time it takes for an object from the ground to hit its maximum height will be the same for the object from its maximum height to hit back to the ground, right? It makes sense, because if I throw this pen, right, it goes up and it goes down. These two motions should be perfectly symmetric, right? So I can leave you as a homework to prove that it is true, and I will not show that here. Alright, so if it is symmetric, well, it is very easy. The time it takes, well, is just 2 of my t0. Well, t0 is just the time of the half of the journey, right? So which half should I calculate here? Obviously, the later half. Because the later half, the object is initially at its maximum height and it falls to the ground, alright? So it's very easy. So initially at its maximum height, it has no velocity. So its velocity is 0. So let's investigate about this section. How long does it take for the apple from its maximum height to fall back to the ground? Well, I know that when it falls back to the ground, its vertical velocity, since it's symmetric, will be the same as my initial vertical velocity when I'm throwing it up into the air, right? So this is my vertical velocity. This is also my vertical velocity, right? So what's the formula for the velocity we've talked about in SUVAT? Well, it is that my vertical velocity is essentially equal to the initial vertical velocity times the acceleration plus the acceleration due to gravity times time, right? So this is formula we talked about in the last video. If you don't know it, you should go watch it. Otherwise, you will be feeling very confused. Okay. So here comes a very convenient part. Since I'm falling from the maximum height, which my object is almost stationary, it is stationary at the maximum height. So its velocity is 0. So I don't have an initial vertical velocity, right? So my vertical velocity is just equal to the acceleration due to gravity times the time. And what's my vertical velocity? Well, it is just equal to my velocity times the sine of the angle times the sine of this angle theta. I've talked about it. Remember this triangle? You should remember this triangle. This is the vertical velocity, all right? So v sine theta is equal to gt. Well, tell me what is t then? T is equal to v sine theta divided by g. And now I have calculated the time which it takes for the object to fall from its maximum height to the ground. Well, what is my actual time then? Well, it will be just 2 times that. Well, it will be equal to 2v sine theta divided by g. And remember, we are calculating our range, right? And I've said the range of the object, the distance it covers, is equal to the horizontal velocity times the time. Well, now I've calculated time, and now that I know the horizontal distance of the object is its actual velocity times the cosine of the angle, cosine of this angle, and now I want to time the time. I want to multiply by the time, and the multiplication and the time, the value of the time, I already have it, and I just plug that into the formula, and it will be equal to 2v sine theta divided by g, and I combine those together. I want to know the range of my object will be equal to 2v squared divided by g times sine theta times cosine theta, right? Times sine theta cosine theta. Right. So if you have learned about further trigonometry, what is 2 sine theta cosine theta? Well, it's just, sine of 2 theta times v squared over g, right? So I know that the distance of the object in projectile motion is precisely equal to sine 2 theta times v squared divided by g. And now I want to ask you a very interesting question, right? So assuming I am applying the same force when I throw an object, I'm applying, let's say 10 newtons, right? So at which angle I throw the object will it cover the furthest distances, right? So, if I throw it at 30 degrees, it surely will travel a lot faster in the horizontal direction. However, it will have a lot of less air time. And if I throw it up this 60 degrees, well, it will cover more time in the air. However, it will travel insanely slowly on the horizontal level. So what's the compromisation point? What's the optimal point which I should throw this object to make it go the furthest distance? Well, if you look at this formula, you will see the answer is 45 degrees. So if I throw 45 degrees, the object will cover the furthest distances. And the reason is that the sine of 2 times 45, which is sine 90, is equal to 1. And 1 is the maximum value a sine function can have, right? So if I plug in any other value, this value will be less than 1. Thus, the distance I'm covering will be less. So if I throw it at 30 degrees, well, this is sine 60, which is equal to 2 over root 3. So I'm essentially lowering my distance, all right? So that's a very interesting thing you may want to remember, all right? All right, now let's actually take a closer look to the vector componenting in projectile motion. All right, so for vertical velocity, I can decompose it into the horizontal section, which is v horizontal, and the v vertical section. All right, so the v vertical. And an interesting thing about this is that these 3 vectors can form a triangle, all right? And this is the v horizontal, this is the v vertical, and this is the actual velocity, right? So, and if I call this angle theta, very interesting thing in trigonometry tells us that if we are calculating the magnitude here, the magnitude of the vertical velocity squared plus the magnitude of the horizontal velocity squared, and we take the root of that, will be equal to my actual velocity. So that's the Pythagorean theorem. All right, so we've taught that in middle school. And also, if I look at it in the vector perspective, my velocity vector will be equal to the horizontal velocity vector plus the vertical velocity vector. Right? So this is the essence of vector componenting. And my vertical velocity will be equal to my actual velocity times the sine of the theta, and my horizontal velocity will be equal to my velocity times the cosine of the theta, right? So this is the theta, and cosine of the theta, v times cosine of theta gives me horizontal velocity, v times sine theta gives me the vertical velocity. Okay. All right, now let's investigate about what's the highest point that the object can reach. All right, so this will be very easy since I know, at the highest point, the object just directly falls to the ground. So that's basically one-dimensional motion if we look at it in the vertical perspective. All right, so the h max will be precisely equal to 1/2 times g times t squared, which it takes the t squared, which the t here is just the time it takes for my apple to fall from the highest point to the ground, right? So at this point, I'm not considering about the horizontal aspect about my velocity because it is essentially not related, because I'm calculating the vertical distance, which is the height, and that the height is not related to anything about horizontal. All right, so h max equals 1/2 times g times t squared. Well, I already have my formula for t here, and I can just plug that in. Well, h max will be equal to 1/2 times g times t. And remember, the t is only 1/2 of the time of my actual airtime of my apple. So I need to take the 1/2 value of this t to get the t of this value, which I need to plug it in. So 1/2 times g times v sine theta divided by g, and I square it, which will be equal to 1/2 times g times g squared v squared sine squared theta, and I can cancel these two, and I'll get my h max, my maximum height, will be precisely equal to 2g v squared sine squared theta. All right, so let me write that down. All right, and the final thing we're gonna investigate is my final velocity when I actually hit the ground. Well, because projectile motion is symmetric, the final velocity will be just equal to my initial velocity. And that is it. That's everything about projectile motion. However, there is one last thing. If the sea level, the horizontal level which I throw the object is not the same as the level which the object lands, these formulas, they cannot directly be applied. You need to think about the situation, and you need to analyze the situation based on the specific part about this question. For example, if I want to calculate the velocity that the object finally hit the ground, well, the final velocity will not be equal to the initial velocity, right? So how do I do that? Well, the final velocity will be equal to initial velocity at the same horizontal level. So I can just make an extensional imaginary line, and the velocity of the object at this point will be equal to its initial velocity, and I can calculate the actual final velocity of the object just by using our SUVAT equation and apply it in this interval. So my final velocity is equal to my initial velocity here, and plus the time which it takes for the object to fall between those two heights, plus the acceleration due to gravity times the time, right? So these are the kind of stuff you need to analyze yourself, right? So this is everything you need to learn. This is everything you need to learn about the projectile motion, and the wing is getting big. So I'm gonna see you in the next class. All right, thank you for watching. Bye bye.